us continue our discussion on NP completeness. So the focus is on designing non-deterministic algorithms. We shall see how to design algorithms, what steps one has to follow in designing non-deterministic algorithms and things like that. Let's define a couple of classical problems which we shall be using as part of our discussion. The first problem is called CLIQUE. For this problem, input is a graph G and say an integer K. So the question is this: does there exist a clique of size say K? Okay. So to answer this, first let's understand what is a clique. It is a completely connected subgraph of G. We have seen this in the context of graph algorithms, but let's revisit. Which means, formally if you write, it is a subset of vertices such that for all u comma v in S, you see that there is an edge between uv. So it's a subset of vertices such that if you take any pair in S, there is an edge between them. Correct? So that's precisely is a clique. And if you ask for a clique of size K, then cardinality of S is K. Okay. And there are two versions. One is exact version, wherein you ask for clique of size. Okay. Suppose clique is a set of vertices. We ask for clique of size this. And the other one is at least version, where you ask for clique of size at least K. Okay. And so whatever discussion we will be having, it is applicable for both. So now let's look at an example so that you have clarity on this definition. Suppose you have a graph like this. Now you see that 6, 2 and 5, they form a clique of size 3. Okay. Now if this clique represents the set 2, 5, 6. And the other thing is, and this is also known as K3. This is the notation we follow, right? And this graph has a clique of size 2, and each vertex is a clique of size 1, something like 1, 5. They are all clique of size 1. And this graph does not have a clique of size 4. There is no K4 in G, no clique of size at least 4. Fine. Now one may ask this question. Let's assume this is G. So input is G comma say K equals 3. The solution to this is yes, because the question says, does there exist a clique of size K? Answer is this. Now you ask G comma K equals 4 and you return no. Suppose it is at least version, then when you pass the input g comma k equals say 2, so the question is, does there exist a clique of size at least 2? Answer is yes. Reason, say 2, 3, 5 forms a clique of size at least 2. And not just that, you look at say 4, 5, they form a clique of size 2. So it's a subset of vertices which is fully connected. You look at a pair, there is an edge between them. Now you are given an arbitrary graph and an integer k. In the exact version, we are interested in knowing what is the answer to this. Does there exist a clique of size k? And in at least version, we are interested in knowing does there exist a clique of size at least k. Fine. So now, what is the complexity of this question? Can this question be answered in polynomial time? So, question is this. So, does there exist say order n power 4 or order n power 10 algorithm to solve this? So, that's the question we always ask. Given a problem, can you come up with a solution of this type? What are these? These are all deterministic polytime algorithms. So can we discover a deterministic polytime solution to a problem like this? Fine. Let's look at the complexity part of it. Input is g comma k. Question, does there exist a clique of size k? Now here is an approach, or what is known is this. Try all subsets of size k. So you have subsets like S1, S2, like this you try, and how many subsets will be there? You see that there will be n choose k subsets, correct? So you try listing one subset of size k, second subset of size k, and so on up to this. You have a set of size n, and cardinality of v of g is n, and in that you are listing all subsets of size k, and there are nck of them. So L is precisely this. And then what you do, verify Si is a clique or not. Now how do we verify this? We just have to check for all u comma v in Si whether u comma v in this. And we know that cardinality of Si is k, and you look at all pairs in this. So number of pairs in Si is how much? K into this, or this is theta of k square. So at most this many edges can be there. K square edges can be there. So number of edges in Si is at most this. So checking whether Si is a clique or not can be done in how much time? Theta of k square time. And how many SIs are possible? Number of SIs is precisely this, correct? So number of subsets is n choose k, correct? So k can be anything. You ask for a clique of size k, so k could be anything, right? So number of subsets of k is size k is so much, this. So now overall time complexity is, it is n choose k times k square. So this is precisely what we have as far as this is concerned. There are a couple of things to note as a remark. If k is fixed, say 10, 20, 100, then this algorithm runs in polynomial time. So this will be like say n choose 10 into 10 square, and this is theta of n power 10. So n choose k is theta of n power k. Okay. So on the safe side, let me write order n power k. You can verify that it is order n power k and omega of n power k. Therefore, it is theta of n power k. Okay. But when k is a variable in n, so it could be log n, it could be root n, it could be n by 2, then it is not a deterministic polynomial time algorithm. Then you can only say it runs in n power k times k square. Fine. So now in this case it's poly. It's a deterministic polynomial time algorithm. This one is not poly. Okay. Because if k is say root n, then it is n power root n. If k is n by 2, then it is n power n by 2. Okay. And there are additional factors like root n square and n by 2 the whole square and so on. So now you see that we are not getting something like order n square or order n cube irrespective of this. Okay, so note that it is not known as of this date an algorithm like order n cube or say order n power 10 for this problem. So what is known or the current best is only this. So if it is fixed, it is poly, otherwise it's not. So which means it's not a uniform polynomial time algorithm, or it's not a polynomial time algorithm for any value of k. So we still do not have an algorithm of this type. So what is known is only this. Now we are interested in problems like this, and it is not known to have a deterministic polynomial time algorithm. How do we cope with such problems, and is there a difficulty in the computation involved? Can we understand the computation, and what causes this difficulty, or why do we say these algorithms are difficult? And that's something we wish to explore as part of this theory.